All right, so generally speaking, we'll just start with eliminations and some of the key differences between eliminations and substitutions. So eliminations are looking for a beta hydrogen to remove with a base. So that's what I say here, beta hydrogen removal. And this implies that it's an acid-base reaction, which is true. Eliminations involve a base, removing an acidic proton, and then removing some leaving group. So generally, acid-base reactions are faster than substitution. So therefore, if there's competing pathways, if Sn2 and E2, for example, are both possible pathways based on the reaction conditions, E2 will predominate simply because acid-base reactions are faster than substitution reactions. So, and to talk a little bit about the beta position, what we mean by that is we're always looking at the alkyl halide carbon. That is the alpha carbon. So alpha relative to the chlorine. So alpha is the first position adjacent to the halogen. So alpha is this carbon, and then beta would be the second position away from that carbon. So this is alpha, this is beta. So these hydrogens both are beta hydrogens that can then be removed by some base in the elimination type reaction, which involves removal of this base, creation of this carbon-carbon double bond, and cleavage of the carbon-chlorine bond to give you a alkene. This is showing it in a concerted mechanism, which is exclusive to E2, but generally speaking, you're always going to be removing this beta proton, whether it's by a strong base like in E2, or if it's driven by a carbocation stabilization like in E1. So that's a little bit about general ideas of eliminations. And now I'll get into some of the specifics with E2 and E1. So, but I'll pause here if there are any questions and let you guys copy this down if you want to. All right, so first thing we'll talk about then is E2. It's similar to Sn2. I think that E2 makes a little bit more sense because you're not forming that carbocation. So I think it's good to start with it. E2 is a concerted mechanism, just like Sn2, which again, that means that bonds are forming and breaking simultaneously. So that, in other words, that means this is one step. Other information, it's bimolecular. So that means the rate is determined by the rate constant times the concentration of the alkyl halide times the concentration now of the base, not the nucleophile, because in E2, we are having base functionality and not nucleophilic substitution type functionality. So that's E2. And the last unique part of E2 is that you have to have an anti-position, anti-hydrogen to undergo Sn2. So anti-hydrogen is necessary. Okay, so first let's talk about the anti, because this other stuff is consistent with Sn2. So hopefully that makes sense. But the anti position is new. And what this is referring to, if you recall from a Newman projection, let's look at this general example. So if we're going to look down this carbon-carbon bond here, it would put the that carbon in the front. So we have a hydrogen up here, our methyl group, and then another hydrogen. And then here our methyl, this CH2Cl would be in the back. So we'd have this like so. So the anti position is when you have a substituents that are across from each other in the Newman projection. So here, this hydrogen is anti to the chlorine, this hydrogen is anti to this hydrogen is anti to this CH3. So you have to have this type of configuration for E2 to occur. Once you have this configuration, the base can then come in, take this proton, you form the carbon-carbon double bond, which is like between the plane of the board here, and then you kick this out. So what this makes is your alkene product, which in a Newman projection looks like this, which is confusing, so I'll redraw it, but this is how it looks in a Newman. Oops, those should connect like that. And then if you were to redraw this like a normal structure, it would be this, and then the hydrogens are now implied. So you have to have that anti-position. So this kind of means that you need to be comfortable with Newman projections for sure, because you need to be able to notice if it can be anti or not. But there's a few characteristics that you can just quickly identify that will tell you if it can be anti or not. So like if we look at this position, even this carbon that I'm showing here, this molecule is not chiral. So these positions are not fixed. So what I mean is this bond here can freely rotate. It can twist. And by doing so, it can put the chlorine in any configuration that it needs, which means that you can clearly get it so that it would be anti. So if it can be in any configuration, then it can certainly be in the configuration that it is required. So that's the case here. But let's say you have a different molecule now. Say you have this, right? So now in order for it to be anti, you would need a trans hydrogen. So you would need a dashed hydrogen that's beta to the chlorine. So in this case, we don't have that because our hydrogens are wedged, and we have these methyl groups that are blocking the dash position. So no E2 is possible here because we don't have anti, we have no anti-hydrogen. Okay, so pay attention to the stereochemistry there. Again, if it's achiral, something like this, you can have free bond rotation and you'll get to the position. But here, you can still have free bond rotation, but it's always going to end up in which the relationship between the chlorine and hydrogen are going to be syn like this, are going to be cis. The reason for that is because you can't interconvert now because these are they're specific molecules because of the nature of this three-dimensionality that we're representing now when it is chiral. Because if you were to have something different, it would be an enantiomer, which has a different property, or diastereomer in a different case, again, has different properties. So that would that's not possible. But with the things that are achiral, interconverting the positions of the hydrogens does nothing. It's the same molecule because, again, it's achiral. So you have to pay special attention if you have a chiral molecule and you trying to do E2. All right, so that is E2. And I'm not going to show the energy diagram just for the sake of time. It is extremely similar to Sn2. You have one intermediate in which you're breaking and forming bonds at the same time. And then not an intermediate, transition state, I should say, where you're breaking and forming bonds at the same time. And then that transition state collapse down to the products. All right, so now E1 is different. This is stepwise, which again means multiple steps. You will have intermediates in this case. So, and you have carbocation formation, just like Sn1. So what this means is that rearrangements are possible, and you need to be considering that. When the carbocation forms, if there's a more stable carbocation that could form, it'll rearrange faster than the reaction will take place. So you're only going to get the rearrangement product. So let's just look at a specific example here. We have this tertiary alkyl halide. You can then do this in some polar protic solvent like methanol. You're going to get this, you're going to get a mixture here, but this is the E1 product. And then you could also get the Sn1 product, which is the substitution. So a key point to make here is that Sn1 and E1 almost always occur together unless you have very specific conditions that make it such that one of them will predominate. But usually it's going to be a significant mixture, which is why the E1 and Sn1 pathways are usually unwanted byproducts, not necessarily the main focus for the particular reaction. So anyway, to make the E1 product, the mechanism involves first the cleavage of this chlorine spontaneously, which again is, like I mentioned last time, is the hardest part to rationalize in this whole step because it's just a spontaneous bond cleavage. That's not usually something that happens. So you're right in thinking that, because this is extremely unfavorable step right here. But again, usually these reactions are done with a large enough concentration and over a large enough amount of time that some of the chlorine can leave, and then you'll have some molecules with this carbocation. And as soon as the carbocation forms, you'll undergo these types of reactions, Sn1 and E1. So in E1, the methanol functions as a base instead of a nucleophile. So when it's functioning as a base, it's going to remove this acidic proton. And then at the same time, this hydrogen will cleave, and you get the alkene product. And as another byproduct, you're making protonated methanol, which is this, which can then be deprotonated by this chlorine, but I'm not going to show that just for sake of time. And it's not the product, because here we've explained the product. So if the question was draw the mechanism that explains the product, you could stop here. But if they could have some follow-up question about this byproduct, so you would have to know that. Just depends on the question. All right, so questions about this, about E1? All right, if there are no questions, we'll get into a whole bunch of questions to see how you can look at the reactor conditions and determine what pathway is most likely. So first, let me show you my table, which hopefully you all have, but I need to explain a few things about it. So here's the table. So the first thing to notice is your substrate, which is either primary, secondary, or tertiary. It can also be benzylic or allylic or some of these other things that we'll talk about as they come up in problems, but they fit in these substrate identities fairly well. So the first thing to point out is we need to be able to identify what's primary, secondary, and tertiary. So remember, primary is just something that's has an alkyl halide that's only has one carbon bound to it, substituted by one carbon. Secondary is this one, and tertiary is this one. So again, this carbon has two other carbons, this carbon has one, this carbon has three other carbons. And that's where we get primary, secondary, and tertiary. So once you have that, it's important to notice a few things. If you have a primary alkyl halide, it's extremely likely that you're going to get Sn2. Because if you look, 4 out of our 5 options are Sn2 with a primary alkyl halide. So your general assumption, regardless of any other conditions, is if you have a primary substrate, that it's probably going to undergo Sn2. There's certain cases where you can have a strong base and a weak nucleophile in which E2 will predominate, and we'll talk about those. But as a general rule, it's good to you can eliminate many of these options just by knowing the substrate concentration and not getting confused and overcomplicating it with the other stuff that's involved. Now, if you have a secondary alkyl halide, you're in trouble because you have to know the other stuff to determine what's going to react. Because if we look here at our options, we have E2, Sn2, E2, Sn1, E1, and Sn2. That's all of the possible pathways. So the only way you will know which one will predominate is based on the identity of the other reagents. And similarly to primary, if you have tertiary, E2 is more likely, again, if you have a base. If you don't have a base, then you're going to form a tertiary carbocation, which is Sn1, E1, which is the other 3 possibilities. So the point of tertiary is you can't have Sn2. It's impossible. So if you see a tertiary center, doesn't matter what the other conditions are, it won't be Sn2, which is important to recognize, because then you can just eliminate some possible pathways simply, again, based on the substrate's identity. Okay, so that's that. So now this table is only worthwhile if you can identify what's a strong nucleophile or a strong base or both or all these conditions. So the next thing we'll talk about is how you determine what's a strong base, what's a strong nucleophile, and what are some of these features that you're looking for. So generally speaking, again, there are always exceptions, but generally these rules work pretty well. something will act as a nucleophile if it is a small molecule and a large atom. The reactive center is a large atom. And the bases are the opposite. If you have a large molecule, but a small reactive center, small atom. So again, you need to know the difference between a molecule and an atom for this to make any sense. So remember, a molecule is the collection of atoms bound in a particular structure. So if we look at this example, the molecule is pH 3, where you have 4 atoms, 1 phosphorus atom, and then 3 hydrogen atoms. So the atom is the single element that is bound in the structure, and that structure makes up the molecule. So this is an excellent nucleophile because the reactive center is a large atom. It's phosphorus. It's in the third row actually. So it's much larger than like oxygen or nitrogen. So this is an excellent nucleophile because it's a large atom. This is a small molecule because these hydrogens are small. So this is an excellent nucleophile. This would be a strong nucleophile and a weak base. It's a weak base because it is the opposite of the base conditions. It is a large atom and a small molecule. So that makes it's suggestive that it's not going to act as a base. Okay, another example of nucleophile is something like sodium thiolate. So the reacting center is this sulfur. This sulfur, again, large atom, larger than oxygen because it's also in the third row. And it's a small molecule because it's only substituted by a hydrogen. So this is similar to like hydroxide, except it has sulfur, which makes it a better nucleophile and a worse base. So this is a strong nucleophile and a weak base. So if you look at my table now, this would fall under this row here, this column rather, where you have pH 3 or SH minus are strong nucleophiles and weak bases. So if you have a primary or secondary substrate, you're going to get Sn2 from those pathways. If it's tertiary, then Sn1 is the only option, Sn1, E1. All right, so now some bases are something like T-butoxide. Oxygen is a small atom. It's in the second row, so that fits here. It's a large molecule because these methyl groups are huge. Relative to the size of a hydrogen, methyl group is like 100 times as large, as takes us that much more space. So because of that, this T-butyl group makes this molecule extremely large. So this is going to function as a base and not a nucleophile because of the steric hindrance. So this is a strong base, weak nucleophile. Okay. Another example could be like this nitrogen compound. Nitrogen, relatively small atom, large molecule because it's substituted with these ethyl groups. So again, strong base, weak nucleophile. So now these would be in this column here, which if you notice is always E2, regardless of the substrate, it's going to be E2. And again, combination of reasons for that. You need a base for E2, and acid-base reactions are faster than substitution. So if you have a really strong base, but it's not that good of a nucleophile, E2 is always going to predominate as the pathway. Okay, now these ones are relatively straightforward because they fit these rules perfectly, but there are other molecules that don't fit the rules, and then you need to assess what's going to happen in those cases. So let's look at some cases that you have this overlap. So if you have like sodium hydroxide, this is a nucleophile and a base. And the reason for it is oxygen here, small atom, suggestive of a base, right? So small atom, that equals base, or suggestive of base function. But this is a small molecule because it's just substituted by hydrogen, right? So this is suggestive of a nucleophile, right? So what this is a strong base and a strong nucleophile. So the identity of the substrate will determine what pathway is going to predominate in a case like sodium hydroxide. And this is the first column in this diagram here in my table, where you have strong nucleophiles, strong bases. Primary is always going to be Sn2, but any other case is going to be E2. The reason in secondary alkyl halides, when you have this ambiguous reagent, you get E2, is again because acid-base reactions are faster than substitution. So given the option, substitution occurs. On a primary center, acid-base reactions are still faster, but the substitution will predominate simply because of the thermodynamics of that case. So this type of column you just kind of need to know, because the general rule of acid-base reactions being faster doesn't really apply for the primary alkyl halides, again, just because it's susceptible for Sn2. So this is kind of my first assumption that I said, when you see a primary alkyl halide, you should always think Sn2, unless there are reasons that it couldn't be Sn2, which is like this column's case. All right, let's look at one more type that could be either. Let's look at NH2. We've seen this. This is amide. Again, small atom, suggestive of base. Small molecule, suggestive of a nucleophile. So this is both a strong nucleophile and a strong base. So again, this would depend simply on the substrate and maybe the solvent to see what is going to predominate, what pathway will predominate. Okay, now you'll notice that I haven't talked about polar protic or polar aprotic solvents yet, because you should consider solvent effects as the very last thing that you should consider, because all this other stuff is much more telling for the type of mechanism that's going to happen, because you can do an Sn2 reaction in a polar protic solvent. It's not a requirement that it has to be polar aprotic. It's just that Sn2 is preferred in polar aprotic solvents, but it's not as simple as that would dictate what pathway predominates. So again, as a reminder, polar protic solvents can have hydrogen bonding with themselves. Polar aprotic solvents cannot. So polar aprotic is like acetone and dimethylformamide. So let me write some of these. So polar aprotic, acetone, dimethylformamide. Polar protic is like all alcohols and water primarily. There are others, but this is what you'll see the most. So I'll just say ROH and water, right? Because they can have hydrogen bonding with themselves. You could also have carboxylic acids, but they can do some interesting chemistry because of the nature of the carbonyl. So I'll include that, but it's much more common to just see alcohol or water. All right, so that was a lot of stuff, but hopefully it's starting to make sense. Are there any questions about any of this? Because now for the rest of the time, I have like, I don't know, a dozen questions or so. Try to get through as many of them as possible and go through this stepwise to assess what pathway will predominate based on the reagents. All right. No questions, so let's move along. So we'll start with, let's see what I got here. Yeah, we'll start with that one. Seems good. So we have a cyclopentane. This is a good example to start with, I think, because it illustrates a few points. So first of all, we have to identify the substrate. It's the best way to go about this, in my opinion, is always identify what your substrate's substitution is, because that will eliminate some pathways potentially. So here we see this as a primary, right? This center with the one that's bound to the halide, is only bound to one carbon. Well, that carbon is bound to a bunch of other carbons, but we don't care, right? We're interested in just the alpha carbon, which is primary in this case. So that is suggestive of Sn2, like I first mentioned, just because most of the situations with Sn2 or with primary will result in Sn2. But this is an extremely large molecule with a small atom. So this is an excellent base. This is a strong base and a terrible nucleophile. It's a terrible nucleophile because the T-butyl group, these methyl groups, prevent the oxygen from approaching the alpha position. So because of that, it can't undergo the substitution type pathway. So this is definitely going to be E2. So now we can look at the table to make sense of this, but what I described is what you would arrive at the table. So the way I would do these types of problems at the beginning is have a printout of this, or you copy it, or however you want to do it, but have this available with you and then get comfortable with recognizing, is the reagent strong base, weak nucleophile, or whatever it is, be able to recognize that and then look at the table. And if you do that enough, if you do enough practice problems with that, you'll just basically memorize the table without even just like having to try to memorize it, because you'll just recognize the patterns, because it's always consistent once you begin to get that pattern recognition. So here it's a strong base, weak nucleophile. So that's here, it's primary, so E2. So like I said, it's suggestive of Sn2 because of all these other possibilities, but due to the nature of the reagent, E2 is the primary pathway. So now, knowing that, we have to look for a beta hydrogen, because if there isn't a beta hydrogen, then E2 is not possible, and we're done. There's no reaction. And you will see some questions that have no answer. So you just always have to be skeptical. So here's our beta position. We have this hydrogen. Is this hydrogen anti to the chlorine? Well, this is a chiral, so it can be in any position it needs to. So it can be anti. So then our base would attack. Let's erase our primary position now. Base will come in and attack the hydrogen. And then you'll get the alkene formation and the cleavage of the chlorine. So you end up with one product, which is this substituted, disubstituted alkene. And then you'll get potassium chloride byproduct and T-butyl alcohol, which is when this T-butoxide takes the hydrogen. That's what makes the OH here. All right. Questions on that? Am I going too quickly, or is this kind of making sense, or any comments? All right, cool. Thumbs up. All right, so let's look at another example. So let's see here. Let's do this one. All right. So again, I think it's best to start with the substrate identity. So if we look at our substrate here, we have secondary alkyl halide. It's substituted by this ethyl group and then the methyl group here. And then we just have a hydrogen. So secondary is the hardest case, right? Because secondary can be anything. It depends entirely on the identity of the other stuff in the reaction conditions. So this is water. So this is a weak nucleophile and a weak base. And we don't have a case for that on our sheet. And the reason for that is whenever you have a situation like this, this is just a solvent. So this is now going to be dictated by the identity of the solvent. Well, this is polar protic. So this is going to be Sn1 with a little bit of E1, primarily Sn1. So the reason we can tell that this is a weak nucleophile and a weak base is usually if you don't have a charge, that is suggestive that the molecule is a weak nucleophile and a weak base. There are some exceptions, like my phosphorus trihalide or what I can't remember the name of this, but this molecule that we started with, the pH3, this has no charge, but it's still an excellent nucleophile because this is a large atom. Well, here in this case, this is not a large atom and it's a small molecule. So that makes it have properties of both, and both a base and an acid, or a base and a nucleophile, but it doesn't doesn't have a charge. So because of that, it means this is a pretty weak nucleophile and a pretty weak base, and it can be a solvent. So it's polar protic. So this is going to be Sn1 or E1. So hopefully that kind of makes sense. It's the process of elimination when you get to stuff like water, just because it doesn't have obvious nucleophilic or basic properties. So because of that, it has to then fall into the category of solvent effects. So because of that, then our Sn1 product is where an OH group will replace this. And our E1 product is where you get the alkene between this carbon and this carbon, or this carbon and this carbon. So those are by far going to be minor. So this will be our major product, and the minor products are these two. But if the question was what's the major product, you wouldn't even need to recognize that the E1 pathway was possible. So I just want to be complete here. And water usually doesn't participate in formation of E1. So the minor products there would be very, very minor, but they still form. So it's good to include depending on what is specifically asked. All right. Questions on this one? All right, let's look at another one. Okay, always start by identifying your substrate. So here we have primary and alkyl halide. That's very suggestive of Sn2, just like our first case. Here we have a small atom, so that is suggestive of a base. And it's a relatively small molecule because this is just an ethyl group. It's not something like a T-butyl, so it's relatively small. So this is a strong nucleophile and a strong base. However, this is primary. So the fact that this is a nucleophile and it's primary, Sn2 will predominate, right? So let's look at the chart. But here we have a primary substrate, strong nucleophile, strong base, Sn2. So when Sn2 occurs, you get a substitution of this oxygen group with the bromine, and that makes this. Did I count my carbons right? 1, 2, 3. I didn't. Oh, no, I did actually. Yeah, okay. And this is the Sn2. And again, in this case, you would get a minor byproduct of the E1 or E2 rather. But again, depending on the question, you may or may not need to include that. Yeah, this would be the E2 product, which is minor. Here's your major Sn2. So if you wanted to do this reaction in the lab, you would try to optimize it such that you would get a smallest amount possible of the E2, which could be dictated by solvent effects or reaction parameters. Maybe you do this in cold temperature or et cetera. But I doubt you'll be asked about those specifics, but just let you know that are things that you can control depending on some of the other reaction conditions. All right. Questions on that? All right. This next one we'll do, it's more challenging. Okay, so again, recognize your substrate. Our substrate is secondary, right? Because this carbon is only substituted by 2 carbons. So that means it could be any possibility. We also have a weak nucleophile and a weak base because this is a alcohol, so it's not likely to function as a nucleophile or a base, but that means it's a solvent. So this is polar protic. So this is likely Sn1 or E1, combination of those two. So now the question becomes, is our carbocation subject of rearrangement? And in this case, the answer is yes, because we have this hydrogen that's adjacent. This is a secondary carbocation. It can easily rearrange to form a tertiary carbocation with that hydride shift. So that's going to happen. And this is going to be your primary carbocation in situ. So because of that, this will dictate the product. So you can either get the Sn1 product, in which the OH of the alcohol would attack the carbocation, and you, after deprotonation, which I won't show just for time, you would get 1, 2, 3. Yeah, you'd get this product. That would be the Sn1 product, which will be major. And then the E2 product is removal of this hydrogen or one of these hydrogens from this methyl or that methyl. They would give the same compound. So the E2 products then, since they're byproducts, I'm not going to show the total mechanism just again for time, but this is one of them. And then the other is this one. Now keep in mind, this one, this top one is by far going to predominate if this was the major pathway, because it's substituted more, which means this is more stable. Remember, we talked about stability of alkenes. The more substituted the alkene, the more stable it is. So here, this would be more stable of these two. So that would predominate if there was a choice for the molecule. But in this case, this is the major pathway and the major product by quite a bit. So the reason I talk about the carbocation rearrangement is you may incorrectly say, based on the reaction conditions, that this is the product, because you've recognized that it's Sn1 because of polar protic, E1 will be a minor product, all the stuff we just talked about, but you've missed the rearrangement. So this is completely wrong. You're going to get almost none of this product, because as soon as you form this carbocation, it will rearrange faster than the reaction will take place at that center. So this is going to be an extremely small amount, like, I don't know, less than 5% of the product are going to be this one. So this would be a challenging multiple choice question where they have this answer and this answer. This one is by far more likely. All right. Questions on this one? All right, let's look at another one that points out how don't use the table too much as a crutch, because it'll get you into wrong answers if you're requiring the use of the table. So at the beginning, I encourage you to use it, but you have to do enough practice that the table becomes second nature almost. So here we have a secondary alkyl halide, and then we'll react this with sodium bromide and like acetone. All right, so it's secondary. So again, this is the ambiguous case. It can be all of the possible reactants, or it can be all the possible pathways. So we have to determine what is most likely. So this is secondary. This is Br minus is a reactive species. This is a terrible base. We know it's a terrible base because HBr is a strong acid. So its conjugate base is Br minus, and that's terrible, right? Remember, acids and bases have this relationship where if it's a strong acid, its conjugate base is weak, and that's the case here. So that means that Br minus is a terrible base, so it's probably a decent nucleophile. So, say Nu. All right, so if it's a nucleophile, that would be suggestive that this is going to be Sn2, right? If we look at our table, this would be a strong nucleophile, weak base, secondary, so Sn2. And it's polar aprotic solvent. This is acetone, can't have hydrogen bonds, polar aprotic. That would be suggestive also of Sn2. So you'd think that your product would be this one, where the bromine comes in and replaces the fluoride. And remember, Sn2 undergoes inversion of stereochemistry, so you would replace the wedge with a dash. But however, this is wrong. Oops. All right, we're back. So this is incorrect. And the reason this is incorrect is because of the identity of the leaving group. So we know that HF is a weak acid, right? So that means that F minus is a relatively strong conjugate base since its acid is weak, which means that F minus, horrible leaving group. So if you have a horrible leaving group, none of this stuff will happen. You're not going to get a E1, you're not going to get E2, you're not going to get Sn2, you're not going to get E1, you're not going to get Sn1, because you need the leaving group to leave. If it's a terrible leaving group, you're not going to get anything. So the only answer for this question is no reaction, even though our table would suggest that it is going to be Sn2. You need to recognize that the leaving group needs to be of suitable quality for any of this stuff to occur. So this is kind of a precursor that you should just always be thinking about as you're going through this, which is my point is don't rely so heavily on the table because there are factors like the leaving group that you can't really include in a table. So you just gotta, I just want to point this out so that you're thinking about it when you get asked questions like this. So, right, any questions on this one? Looks like we time for one more maybe. So let's do that one. Okay, so let's say we have this. All right, so we have secondary alkyl halide, this position. We have just 2 carbons substituted there. This is a strong base and a weak nucleophile. Again, because this is a small atom, large molecule, that's very suitable to be a strong base. So because of that, this is probably E2. So again, we can look at our table to confirm this, but we have a secondary substrate, and it's a strong nucleophile, it's a strong base, a weak nucleophile, that's E2. So it will be E2. Now, to predict the product, we need to keep in mind that this has to be an anti-hydrogen, right? So this is kind of going back to the beginning of the recitation. We have to consider the positions of our beta hydrogens. So this hydrogen is beta, but it is syn to the bromine. This hydrogen is beta and it's anti to the bromine. So you're only going to get one product, and it's the product in which this hydrogen is removed. This one can't react because it's not anti. So your only product is this one, right? This is the only product. And again, it's because of the antihydrogen, right? There is no antihydrogen at the other position. Therefore, this E2 mechanism is only possible at one of the two centers, even though it seems like we have two beta hydrogens, which would be suggestive normally of two different products. We don't have that luxury in this case because one of the hydrogens is not anti, and that is a requirement for this type of reaction to occur. All right, so any questions on anything, really? We have just a few minutes. I don't want to cram in another question, so I'll just stick around if you have any questions, but otherwise we can end a little bit early today.
I have a question.
Yeah.
So I know how you figure out if it's a strong or weak base, but how can you tell if it's a strong or weak nucleophile?
It depends on the size of the nucleophile, right? So if it's a small atom, that would be a base. So my mistake. But a nucleophile, remember, is large atoms and small molecules, right? So the typical examples are like these two that I started with. But if you mean in this specific case, the reason this isn't a nucleophile is because it is a large molecule, which is the opposite of what makes a good nucleophile, and the oxygen is a small atom, which again is opposite of what makes a good nucleophile.
Okay, so what's like the cutoff then for like a large molecule or like an atom? Because oxygen's like in the first row, right? And then the pH3, the P is in the third row. So what if you found something like in the second row? Like, would you consider that a large or small?
Well, oxygen is actually in the second row, right? Because you have hydrogen and helium is the first
Oh,
row,
yeah, yeah.
right? So oxygen, anything really in the second row would be considered small, and anything in the third row would be considered large in terms of atomic size. In
Mhm.
terms of molecular size, that gets a little bit more ambiguous. So it really just kind of depends because like an ethyl group. So let's compare this, for example. And then like this. All right, so these are our four options that I'm talking about here. So these two, this one is huge
Mhm.
first. Let's start with that one, right? Because you have these T-butyl groups. T-butyl groups are extremely demanding on space. So would be an extremely large molecule.
Mhm.
And then on the other side, this one is hydrogens. So this would be pretty small. Now, both of these are going to be kind of in the gray area because ethyl groups aren't that big, methyl groups aren't that big, again, relative to each other. So these would both be like, I would say, medium size. So you wouldn't be able to tell that this is going to be a nucleophile or a base based solely on the substituents here. There will be other stuff in the reaction that will tell you, be suggestive that it's going to be a nucleophile or a base.
Okay.
So, but if you have these like polar extremes, then you know that this is much more likely to be a nucleophile. This is much more likely to be a base, even though they're somewhat in the ambiguous area.
Okay.
So, does that answer your question?
Yep.
Okay, great. Anything else?